today we will do binary circuits or digital circuits. Now digital circuits can be of two types, combinational circuit and sequential circuit. In sequential circuit we must use the memory as because the output of a sequential circuit at any state depends upon the present state inputs as well as the previous state outputs. But in case of combinational circuit, we must not use or we may not use the memory because the output at any state depends upon the present state inputs only. It doesn't consider previous state outputs. Now the very first one of combinational circuit is an adder. Now what is an adder? That will add binary digits. Adder can be of two types, half adder and full adder. In half adder we just add two present state binary digits, right, or two present state binary bits. It is not considering any previous state carry forward. So this is half adder. It will just add two binary bits of present state. Now if the two binary bits or two binary digits of present state is added along with the previous state carry, then that will be a full adder. Today we will do half adder only, and in the next class we will cover full adder. Now suppose we add two binary bits. So suppose we add 0 plus 0. Then what will be the sum and what will be the carry? If we add 0 plus 0, then 0 plus 0 is what? In decimal, that is 0. So if in decimal this is 0, then what will be the binary equivalent of this decimal? 0, 0. Right? So this is sum and this is carry. This is how you must remember or you must understand. Suppose we add 0 plus 1. If we add 0 plus 1, then that is, if we consider in decimal, this is nothing but 1. So 1 in binary, if we convert in binary, then that is 0, 1. So this is sum, this is carry. Now suppose we add 1 plus 0. Now 1 plus 0 is what? 1. If we convert in binary, that is 0, 1. This is sum, this is carry. Now if we add 1 plus 1. Now 1 plus 1 is 2. In decimal it is 2. So if we convert in binary, then 2 will be 1, 0. 1, 0 is the binary form of decimal 2. So this is sum and this is carry. So this is an easier way to understand the addition. Now we will put these things in a truth table. What is a truth table? Truth table is nothing but a relationship between inputs and outputs. A set of input and output. That means for a certain set of inputs, what should be the output? That is the truth table. While we are designing a circuit, a combinational circuit, then we must go through certain steps. The very first step is the truth table, and the second step is we must form the K-map from that truth table for each possible outputs, and the third step is from K-map we must have the minimized expression for each output line, and the fourth or the last step is we must draw the circuit or we must design the circuit from the derived expression from the K-map. Now the very first step is what? The very first step is to do the truth table. Now while we are doing the truth table, so truth table is what? The relationship between inputs and outputs. So what are the inputs here? Inputs are A and B. These are the two inputs, two binary digit inputs. And what are the outputs? Carry and sum. So this is the first step of designing a combinational circuit, that is truth table designing. Now we will put how many possible combinations of A and B will be there? As there are two input variables, so number of possible combinations will be 4, because 2 to the power of number of input variable, that is the number of possible combinations. So those will be 0, 0, either A, B both are 0, 0, 1, that is A is 0, B is 1, 1, 0, that is A is 1, B is 0, or both are 1. These are the possible combinations. Now for each of these possible combinations, what are your outputs? For 0, 0, as we have already done, sum is 0, carry is 0. For 0, 1, sum is 1, carry is 0. For 1, 0, sum is 1, carry is 0. For 1, 1, sum is 0, carry is 1. So this is our truth table. Now from this truth table, what is the second step? Second step is we must have the minimized expression for each output lines. Now here how many output lines are there? Here there are 2 output lines. One is for sum and another one is for carry. So we will do K-map for both sum and carry, and from that K-map we will derive the minimized expression for both the output lines sum and carry. Then finally we will do our circuit by using those derived expressions. So in the next step, in the second step, we will do the K-maps. So what is the second step? Second step is doing the K-maps. Second step is K-map. Now, while we are doing the K-maps, we will do K-map for both the output lines, right? Now, what will be the number of boxes in the K-map? The number of boxes in the K-map will be 4, because there are 2 input variables, A and B. So what will be the number of boxes? 2 to the power of 2, that is 4. These things are covered in my K-map lectures. Please go through that. I will put the links in the description box. Now, this is the K-map for sum, and we will do the K-map for carry also. This is for sum, and for carry also we will do the K-map. This is the K-map for carry. 4 boxes will be there. Now from the truth table, what was the truth table? For your ease, you can write the truth table left hand side or right hand side in the paper. Now what was the truth table? The sum was 1. For 0, 0 it was 0. Then for 0, 1 it was 1. For 1, 0 it was 1. For 1, 1 it was 0. So 0, 1, 1, 0. Now let us put the box numbers 0, 1, 2, 3. And in which boxes we must put 1? These 2 boxes 0, 1, 1, 0. See, from the K-map, these boxes will have 1 and 2. Because 0, 0 it was 0, and for 1, 1 it was 0. Sum was 0. Now let us come for the carry. In case of carry, what should be the K-map? See, K-map was 0, 0, 0, 1. So only for box number 3 it is 1. For rest all other boxes it will have 0. Right? Now we are putting variable A over there and variable B here. So this row is A bar, this is A, this is B bar, this is B. So what is the minimized expression? The minimized expression for sum will be A bar B. We cannot group because 2 ones they are not following the grouping principle of K-map because they are in diagonal manner. So we cannot group them. So for this one individually we must write the expression for all individual ones. For this one, this is A bar B. What is the expression for this one? This is A bar B. And what is the expression for this one? This is A B bar. So A bar B plus A B bar. That is equal to what? A XOR B. So this is the expression for sum. Now for carry, there is only a single one. So what will be the expression? This row will be A bar. This is A. This is A, this is B. That is A is representing rows and B is representing columns. B bar B. Now all these K-map rules are given in the K-map lecture. Please go through that in the previous lectures. Now this one is the only single one. So what will be the expression for this one? That is AB. So C is equal to AB. This is the derived expression for both sum and carry. Now we will do the circuit. This is our second step. That is, by doing the K-map we have derived the expression for both the output lines. In this case there are two output lines, sum and carry. So by doing K-map we have derived expression for both the output lines. Now we will do the final step is we will do the circuit. So while we are doing the circuit, see what are our expressions? Sum is equal to A XOR B and carry is equal to AB. This is our expression. So while we are doing the circuit, how to do the circuit? There are two inputs A and B. Now for sum, we will just put a XOR gate. So this will give you the sum equal to A XOR B, and for carry just a AND gate. So this will give you C, that is carry, that is A dot B or AB. So this is the circuit diagram for half adder. So this is the process of designing a combinational circuit. Now in the next class we will cover the full adder, and if you have not subscribed the channel yet, please subscribe the channel so that you get the updated contents. Thank you.